All right, guys, I'm going to give you a quick crash course on the concepts of one-to-one and onto linear transformations. And given a linear transformation, a very common question that you'll hear me ask is that transformation one-to-one? Is it onto? Is it both? Or is it neither? And it turns out that just by looking at the dimensions of v and w, you're going to be able to cross off two of those four choices immediately without doing any calculations at all. It's kind of like when we were asking whether a set of vectors was linearly independent, a spanning set, both, or neither. We could always remove two of those four choices very quickly. And the same is going to be true here. It's going to hopefully seem familiar to you. First things first, I need to tell you what one-to-one means and what onto means. A transformation is one-to-one if the kernel of that transformation is simply 0. The kernel is tiny. Actually, this just means that the kernel is 0-dimensional. So if you know that the dimension of your kernel is 0, then you'll also know that it is one-to-one. Similarly, well, not similarly, quite differently, a transformation is onto if the range of that transformation is the whole entire W. Okay? So a one-to-one transformation has a tiny kernel. An onto transformation has a huge range. Okay? So the one-to-one concept is dealing with the kernel of T. The onto concept is dealing with the range of T. And finally, another term that's related to this is the idea of an isomorphism. T is an isomorphism if T is both one-to-one, I often abbreviate one-to-one, just 1-1, and onto. So if the transformation is both one-to-one and onto, then it is an isomorphism. Okay, let's try an example. I'm going to go back to an example that we've looked at before. Let's take T to go from M2 of R to R, and the transformation is simply takes a 2x2 matrix and just spits out A plus D. You might remember, we've done this calculation before, that in this example, the dimension of the kernel of T, turns out it was 3. Okay, so remember that if you replace A with negative D and then you bust out the variables, there'll be 3 free variables to bust out for that kernel, right, when you set the transformation equal to 0. And then also the range of T, the dimension of the range of T was only equal to 1. And again, 3 plus 1 adds up to 4. 4 is the dimension of M2 of R. That's the general rank nullity theorem there. But you'll notice that the kernel is not, it is not equal to the whole V because V is 4-dimensional, right? However, if you look at the range of T, which is 1-dimensional, that is the dimension of W. So the range of T, the fact that it is actually 1-dimensional, means that the range will be the whole real numbers, right? Look at it. Every single real number could come out of a particular matrix. Like, so if you give me a number like 29, I can make a matrix that would transform to 29, right? You could do something like 29, 0, 0, 0. Any real number can be realized as an output of some matrix here. And for that reason, T is definitely onto. The range is equal to the whole entire W. So this is an example of a transformation that is onto, but it is not one-to-one. It is not one-to-one, as it turns out. Okay? Again, with the video, you can always pause or rewind if you need to. I'm going to erase this example and put up another one because I want to keep my definitions on the board for a little bit. Let's look at another example. Let's do the transformation t from, well, let's go from P3 of R to P2 of R, okay? And let's transform this by taking P of x and mapping it to P double prime of x minus 3 times P prime of x, okay? And let's imagine that we did that. You might remember that the kernel of this transformation, we did this one in another video, the kernel is just one-dimensional. So the dimension of the kernel was 1. Okay? The only vectors that are killed by this transformation are the constants. Constant polynomials, which forms a one-dimensional subspace of P3 of R. Now, simply based on that information alone, we can use the general rank nullity theorem if we want to and figure out the dimension of the range. Because remember, these two numbers have to add up to the dimension of V. The dimension of V is 4, but therefore the range would have to be 3-dimensional, and that agrees with W. W is also 3-dimensional, and so again, this is another example of a transformation that is onto, but is not one-to-one. Okay, so we looked at that example earlier. Let's take another one. Let's imagine that we took t from, let me think here what I want to do. Let's do from P2 of R to M2 of R. And what I'm going to do is I'm going to take a polynomial, and to make this 2x2 matrix here, I'm going to output P of 0, P of 1, P of 2, and 0. Okay? You can check that this respects addition and scalar multiplication. It is linear. And so we can talk about the kernel and the range of this transformation. Okay? We can decide which one do we want to start with. Maybe we decide we're going to start with the range. Okay? It doesn't really matter. Let's say we want to look at the range of t. Let's remember how we do this. We take the span of the transformation of a basis for P2 of R. So you have to think of a basis that you like for P2 of R. Well, a very nice one to use would just be different powers of x. So we could take 1, x, and x squared. And what we're going to do here is we're going to transform each of those 3 polynomials using this formula. Now, what is this? How does this formula work? Well, the idea here is that P of 0 just means you're going to plug 0 into your polynomial. Now, this first polynomial is the constant polynomial 1. It's a flat horizontal line, right? That is always equal to 1. I don't care what you plug in for x. The x isn't even a part of the input here. You're always going to get a 1 as an answer. Like if I give you a graph that's just always equal to 1, it doesn't matter what x you plug in, p of x will always just be 1. Okay, no matter where your x is here, this is always just equal to 1. So that is going to be a 1 for sure. But if I take t of x, now what do we do for that? Well, we are going, I'm sorry, I'm still looking at t of 1. If I plug in 1, I still get 1. If I plug in 2, I still get 1. And in the lower right corner, I get a 0. Sorry. So every single entry, when you evaluate the polynomial, is a 1. Now, I was getting ahead of myself. If I want to look at t of x, and I plug in 0 or 1 or 2 for x, of course I'm going to get 0, 1, or 2. Okay, so you're taking this function. F of x equals x looks like that, right? So no matter what input you plug into it, the output is just that same number. Finally, for x squared, we're going to, so for x squared, we're going to square the input. So 0 squared, 1 squared, or 2 squared, and that's going to give you this matrix. What you've got here is a set of 3 matrices. Now you do have to make sure that they're linearly independent. They have to be linearly independent. Let me give you a quick rough idea of why they are. I'm not going to go into the details here. The second and third polynomials, the second and third matrices are not multiples of each other, so they are linearly independent, but notice that they both have zeros on the main diagonal. Here's a matrix over here on the left that does not have a 0 in the upper left corner. So that matrix will not be dependent on the other two, because the other two matrices will definitely create linear combinations that are always 0 on the main diagonal. So this is a matrix that's outside of that. My point being, guys, that all 3 of these, you could check it. You could check it by using the ideas from earlier chapters, but this set of 3 matrices is actually a basis. The dimension of the range is 3. The range is 3-dimensional. The basis has 3 things in it right here. That is not the whole M2 of R. It means that this transformation is not onto. It is not onto. The range is not big enough. You can kind of see that the outputs of this transformation would not give you every 2 by 2 matrix, because the lower right corner is always a 0. Right? So the range comes up short. It does not equal W here, and so this is not onto. What about 1-to-1? Well, if the range is 3-dimensional, can we figure out what dimension the kernel is? Remember, the dimension of the kernel plus the dimension of the range has to add up to the dimension of V. In this case, V is 3-dimensional. So I have a 3 right here, and the range is already 3-dimensional, so the kernel has to be 0-dimensional. The kernel, even without calculating it directly, I know it's 0-dimensional. And that means that this transformation is 1-to-1. It's 1-to-1, but it's not onto. Okay. Now, I had said something before about asking a question where I give you 4 choices, and that you could cross 2 of them off right away. I want to come back to that and just kind of conclude this video with just a quick overview of that. So I could ask this type of question: is T 1-to-1 onto both or neither? This is my famous type of question. You're surely going to get one of these if I ever ask you a question on a test or something like that in the future, for those of you who are in my class. Well, here's the thing. So we have T going from V to W. It turns out, guys, that if the dimension of V, so I'm going to give you 3 bullet points here that are really useful. If the dimension of V is larger than the dimension of W, in that case, T cannot be 1-to-1. There's no chance. It kind of makes sense, because the dimension of the range has to be at most the dimension of W. You can't have a range that's bigger than W, right? So the dimension of the range is at most the dimension of W, which means there's some more left over to be able to add up to the dimension of V, right? The kernel cannot be 0, because if the kernel is 0, then the dimension of the range would have to equal the dimension of V. Let me just write down that equation. I'm kind of waving my hands a lot here, but it's worth just writing this down. The dimension of the kernel plus the dimension of the range is equal to the dimension of V. So again, if W is smaller than V, then the range of T is also smaller than V, which means that the kernel is going to have to contribute something. to make these numbers add up right. And that means if the kernel is contributing something, then you're not looking at a one-to-one situation. Okay? The opposite scenario, oh, and by the way, T might be onto. To figure that out, you're really going to have to look at the range and see if it is equal to W. And again, you could look at the range by indirectly looking at the kernel instead. We know that the kernel is not trivial, but depending on what the dimension of the kernel actually is, that might tell me then that's going to tell me what the dimension of the range is, which would then tell me whether or not T is onto. Right. Okay, the reverse scenario, if the dimension of V is smaller than the dimension of W, then T cannot be onto. V is just simply too small for this to be onto. And T might be one-to-one. Okay, so if V is smaller than W, then T cannot be on. Onto would mean what? Onto would mean that the range was equal to W. But how could V be smaller than W if you're taking W and adding something to it before you get to V? That would be the situation where V is bigger than W. So if V is smaller than W, you can't expect this thing to be onto. T cannot be onto. And finally, last scenario here, if the dimensions are equal, the dimension of V equals the dimension of W, then, and you might have a guess already, then T is both or neither. Okay? It's both or neither. And if it's both, then of course we're going to call that an isomorphism. So for example, so let me take this back off of here again really quickly. If I had T, right, going from P3 of R to M2 of R, I look at that, I say that's four-dimensional, right? And let's just say that so this is both or neither. Whatever I do is going to be either an isomorphism or it's going to be neither. I could take a cubic polynomial and I could spit out just the coefficients A, B, C, and D. That would be a great example of a transformation between these two spaces. And it's very fast to realize that every 2 by 2 matrix is here, okay? It's definitely onto. Or in other words, for the kernel, remember to find the kernel, you set the result equal to the zero vector. And if that was the case, A, B, C, and D would all be 0. In other words, your input that was in the kernel would have to be the 0 polynomial. So this one is an isomorphism. Isomorphisms really means that the two spaces are kind of the same. It's kind of just how you're writing the vectors. Here you're sort of referencing the polynomial through the use of the coefficients that are kind of separated by different powers of x. But at the end of the day, you are keeping track of A, B, C, and D in almost like slots. I hate to call them slots because these are polynomials. Okay, but you've kind of got 4 positions there, and you've got 4 positions here, right? And somehow the way these spaces work is very similar, at least with respect to the vector space operations of addition and scalar multiplication. Okay? But again, just because you have the dimensions being equal here does not guarantee that you have an isomorphism. I could do something like this. I could do T of that thing equals A. And all of a sudden, this is not going to be onto, and it's not going to be one-to-one anymore. It's going to be neither in this situation. So you do have to stop and check whether it's both or neither. But at least you've realize that if it's one of them is, if it's 1-to-1, then it will also be onto. If it's onto, it will also be 1-to-1, and so on. Okay, so these are some properties of transformations I'd like you guys to be thinking about. 1-to-1, onto, both, or neither. This is my famous question about this section, and I hope it makes sense. Do some practice problems. Try it out for polynomial examples, matrices, vectors in Rn. Kind of get the feel of what it looks like and how you are going to make these justifications in different vector spaces. And I think that's the main brunt of what I'm hoping that you'll get out of this section. Thank you very much for your time and attention. Hope it's making sense. Let me know if you have any questions. Thanks a lot, guys. Take care.